Hello and welcome to online lecture number 7 for Chemistry 112 during the spring semester of 2020. We are still in chapter 16. In today's lesson, we're going to focus on various ways of calculating delta G. So for example, if we're asked to calculate the standard Gibbs free energy change for this reaction at 25 degrees Celsius, there's certainly one way we can do that and calculate delta G under standard conditions if we know the change in enthalpy at standard conditions, the Kelvin temperature, and the change in entropy under standard conditions. And we can calculate both delta H and delta S using table values. So for example, we have the delta H formation and the molar entropies for the reactants and products. We can calculate the respective delta H values as well as delta S values and plug those numbers in to our delta G expression. So we use this equation to calculate delta H. This is the same equation you were introduced to in Chemistry 1 that allows us to calculate the change in enthalpy of a reaction from the heats of formation of the products and the heats of formation of the reactants, those table values. And then as we ended the lesson last time with, was we were able to calculate delta S of a reaction from the respective molar entropies of the products and reactants. So those almost identical equations. The only difference is whether we use heat formation values to calculate delta H or molar entropy values to calculate delta S. Otherwise, as we'll see, the actual application of these two equations are exactly the same. Okay, once again, our approach, our plan is to calculate delta G of this reaction at 25 degrees Celsius using this equation. In order to use this equation, we have to be able to calculate delta H using this equation and respective heats of formation values. And then to calculate delta S, we'll use this equation and the given respective molar entropy values. So to plug in our numbers, first delta H is equal to, under standard conditions, the sum of the number of moles of the products times their respective heats of formation values. So that's going to be 1 mole of calcium oxide times its value of negative 635.1. These are all kilojoules per mole, plus 1 mole of carbon dioxide times its heat of formation of negative 393.5 kilojoules per mole minus, so this gives me the total heat formation, sum of heat formation of the products, minus the sum of heat formation of the respective reactants. And there's only one reactant, 1 mole of calcium carbonate, times its heat formation value of negative 1206.9, also kilojoules per mole. So we plug all those numbers into our calculator. What we get is a positive 178.3 kilojoules. So this is an endothermic reaction. So we're going to keep that number in mind. And likewise, we did a very similar calculation, but this time we can calculate the change in entropy of a reaction using the respective molar entropies. So we'll plug those numbers in. So sum of the molar entropies of the products to the same 1 mole of calcium oxide times its molar entropy value of 39.7 joules per mole Kelvin, plus the 1 mole of carbon dioxide, and its molar entropy is 213.6. As you'd expect, a much higher molar entropy because it's a gas, joules per mole Kelvin. That's the sum of the molar entropies of the products. Subtract from that the sum of the molar entropies of the reactants. So just the 1 mole of calcium carbonate times its molar entropy of 92.9 joules per mole Kelvin. Sum of the molar entropies of the products minus the sum of the molar entropies of the reactants. We plug those numbers in. And what we get is a positive 160.4 units of joules per Kelvin. So as we expect, this process does have a positive change in entropy because we're going from 1 mole of a solid to 1 mole of a solid and especially 1 mole of a gas. So now we have our two numbers. We can plug these numbers into our delta G expression. When we do so, though, we want to be careful because we have kilojoules for delta H and joules per Kelvin for delta S. So we're going to need to convert kilojoules into joules for delta H. So that's one approach we could take. So 178.3 kilojoules, of course, is equivalent to 178,300 joules. So that'll be the number we'll use in our equation to make sure the units work out. So we plug our numbers in, get delta G is equal to 178,300 joules minus the Kelvin temperature. This was at 25 degrees Celsius. So 25 degrees Celsius is equivalent to about 298 Kelvin. So minus 298, actually 0.15 Kelvin. 0.15 Kelvin, 298.15 Kelvin, times your delta S value of positive 160.4 joules per Kelvin. We plug those numbers into our calculator. We find is that delta G is equal to 178,300 minus the product of the Kelvin temperature, T, 298.15 Kelvin, and the delta S, 160.4. So we get a value of positive 130,477 units of joules, and we convert that back to kilojoules to consider significant figures, then we probably only have about positive 130 kilojoules. So we calculate that for this process, conversion of calcium carbonate and calcium oxide in carbon dioxide at room temperature, we have a positive delta G, which means at room temperature, this process is non-spontaneous. So because we found that delta G is a positive 130 kilojoules at 25 degrees, this is a non-spontaneous process, and because it is non-spontaneous because both delta H is positive and delta S is positive, and under those conditions, as we learned in the previous lesson, if you have a positive delta H as well as a positive delta S, the process is only going to be spontaneous at relatively high temperatures. So like we did for physical state changes, we have this kind of situation where a process is only spontaneous at either high temperatures or low temperatures, where both the signs of delta H and delta S are the same. Then we can use the same equation that we derived earlier to find the critical temperature above which this process becomes spontaneous. The temperature is equal, that critical temperature is equal to the delta H of the process divided by delta S of the process. So to find this value, as we did before for that physical process, we'll take our delta H value, but keep in mind that if delta S is in joules per Kelvin, we want to make sure delta H is also in joules. So we use our joule number, positive 178,300 joules. Divide that by the delta S value, which is positive 160.4 joules per Kelvin. The joule units will cancel. And what we find then is that the critical temperature above which this process is spontaneous is 178,300 divided by 160.4, or about 1,000, a temperature of 1,112 Kelvin. So for this particular process, above this temperature, that's what we mean by high temperature, above this temperature, we'd expect a negative delta G. As a result, a negative delta G would indicate that this process is spontaneous, but only above this temperature. But there's a simpler way of calculating delta G, and that is using what's called the standard free energy of formation values. You might recall back in our textbook is chapter 6, but in any case, the thermochemistry or enthalpy chapter of chemistry 1, where we were to calculate delta H of a reaction using those standard heat formation values, those table values that describe the enthalpy change associated with the formation of 1 mole of a substance from its constituent elements. So for example, you can produce carbon dioxide, 1 mole of carbon dioxide from the reaction of 1 mole of elemental carbon and 1 mole of elemental oxygen. The delta H associated with that process, by definition then, is the delta H formation of carbon dioxide. So that's a table value that we can use, as we saw in the previous slide, to help us calculate delta H of a reaction, as well as has other applications. In a similar definition, we could also say something about the standard free energy of formation. This is the delta G for a process, but specifically for the process of the formation or production of 1 mole of a substance in its standard state from its constituent elements in their standard states. So likewise, the same process, the production of carbon dioxide, 1 mole of carbon dioxide, it's a reaction. So not only does it have a delta H, of course, it also has a delta G. And the delta G for this particular process happens to be a negative 394.4 kilojoules per mole. A negative delta G, notice it's a spontaneous process. And because this is the delta G describing the formation of 1 mole of a substance from its constituent elements, likewise, that's the definition, the delta G of formation of carbon dioxide. And as we'll see in a couple slides, we can use these delta G formation values in much the same way that we use delta H of formation values. So we take a look at a couple of example delta G of formation values. Hydrogen has a delta G of formation of 0, and that's true because hydrogen is an element. So that's true for hydrogen as well as any other element. By definition, its delta G formation value will be 0. So if it's in the table, it'll be 0. If it's missing from the table, it's missing from the table because it's understood that that value is 0. But otherwise, all of those substances will have either positive or negative delta G of formation values. And what's nice about delta G formation, it actually gives us an idea as to how stable, how thermodynamically stable the substance is relative to its constituent elements. For example, water has a delta G of a negative 237.2 kilojoules per mole. It's a negative number, which means that this process is spontaneous, which means thermodynamically, water is more stable than its constituent elements. The reverse process would have a reverse sign, a positive 237.2 kilojoules per mole. It's a positive number, which means that this reverse process, the decomposition of water into hydrogen and oxygen, thermodynamically is non-favorable. So this process is non-spontaneous. Doesn't mean it can't happen, but it's not going to happen without ongoing effort. And what you'll notice if you go back to think maybe the only appendices in our textbook, look at the actual values, what you find is that many substances have negative delta G formation values. Their substances are more stable thermodynamically relative to the elements. There are some that have positive values, such as nitrogen dioxide. And that's true for not only nitrogen dioxide, but also a lot of other nitrogen-containing compounds. So a positive 51.3 kilojoules per mole would indicate that this process, the formation of nitrogen dioxide, is non-spontaneous, whereas the decomposition of nitrogen dioxide into its constituent elements, I would have a negative 51.3 kilojoules per mole number, it would be a spontaneous process. So nitrogen dioxide, as well as a lot of other nitrogen-containing compounds, are thermodynamically unstable relative to their elements. So as a result, these substances tend to, if ignited, given enough energy to start with, they may very easily thermodynamically break down, decompose into their constituent elements. So as a result, a lot of these nitrogen-containing compounds are part of explosives, because that's what you want, is that the substance to decompose into its elements that produce not only lots of energy, but also lots of gases to produce that very large volume, and if it's kinetically favorable, in a very small amount of time. So we can use delta G formation values by themselves just to get an idea of how stable the substance is relative to its elements. But maybe more importantly, we can also use these delta G formation values in calculations. So in a very similar equation that we saw to calculate delta H and delta S, we can calculate delta G of a reaction simply from its respective delta G formation values of products and its delta G formation values of its reactants. So go back to the same reaction. We have to calculate delta G, and we're given these table values. And we did so in the previous slide, calculating delta H of the reaction using these values, calculating delta S of the reaction using these values, and then using our delta G equals delta H minus T delta S equation. But if we're given delta G formation, another way we can come about this same number is just using delta G formation values and plug those respective numbers into our equation and then get an equivalent answer, as we'll see. So now using this equation, we can find the delta G of this reaction by plugging in the respective delta G formation values. So in a very similar equations, very similar calculation, delta G is equal to the sum of the number of moles of the products times their respective delta G formation values. So we have, once again, 1 mole of calcium oxide times its respective delta G formation value, which is negative 604.0. The units are kilojoules per mole, plus 1 mole of carbon dioxide times its respective delta G formation value, which is negative 394.4. Minus, add up the delta G formation values of the products, subtract from that the delta G formation of the reactant sum. So we have 1 mole of calcium carbonate times its delta G formation value, which is negative 1128.8. And it's also kilojoules per mole. So we plug those numbers into our calculator. And what we would find is a positive 130.4 kilojoules, which to the significant figures that we have, looks like they have 4 significant figures in this case, would in fact be positive 130.4 kilojoules. Which consideration of significant figures is the same number we got from the previous example where we used the delta H formation values and the molar entropy values to calculate delta G by the other method. So you can see we get the same number. That's a lot simpler calculation, but we can only use this calculation if we're given the respective delta G of formation values of the reactants and products. And let's do one more to illustrate the application of this equation. So we calculate the delta G of this reaction, of the reaction of 4 moles of ammonia with 5 moles of oxygen to produce 4 moles of nitrogen monoxide and 6 moles of liquid water. Okay, so we have our equation. We're going to have to calculate delta G, so we can use this equation given the respective delta G formation values. Let's say we're not given the delta G formation of oxygen because oxygen is an element, and because oxygen is an element, by definition, its delta G formation value will always be exactly 0. The same reason why the delta H formation value of oxygen as well as any other element will also be 0. So we can plug in our numbers. We have delta G. This reaction must be equal to the sum of the delta G formation values of the products. So we have, the more interesting, we have 4 moles of NO times its 86.6 number, kilojoules per mole, plus 6 moles of water times its negative 237.2 kilojoules per mole. And then we're going to subtract from that the sum of the delta G formation values of the reactants. So we have 4 moles of ammonia times its negative 16.5 kilojoules per mole plus 5 times the delta G formation of oxygen, rather, which, as we discussed, is exactly 0. So when we plug our numbers in, we find is the sum of the delta G formation values of the products is a negative 1076.8 kilojoules. Subtract from that number the sum of the delta G formation of values of the reactants, which is a negative 66 kilojoules, to give us then a delta G of the reaction of negative 1076.8 kilojoules minus a negative 66 kilojoules, gives us a value of negative 1011 kilojoules. So we can see that's a negative delta G value, which means that under these conditions, that under the temperature which these delta G formation values we determine, probably room temperature, this process is spontaneous because there's a negative delta G value. What is the meaning, if there is any meaning, to the magnitude of delta G? Up to this point, we've only sort of focused on the sign, whether it is negative or positive, but does the actual magnitude have any meaning? And that's when we'll get into the first thing next lesson.